Hello good people, I'm going to solve two problems that involve pH calculations. In the first problem we have a sample of seawater that has a hydrogen ion concentration of 8.9 times 10 to the power of -9. We need to determine the pH value, rounding it to 2 decimal places. And there is a bonus question. What is the hydroxide ion concentration in the same sample? Before I proceed with the calculation, I would like to remind you that in chemistry, these square brackets indicate a molarity. And so this value of 8.9 times 10 to the -9 has a unit of moles per liter. Before I use my calculator to do the number crunching, I'm going to make an educated guess of what the answer should be. Considering that the power is -9, it suggests that my pH should be somewhere around 8. By the same token, if the power was -3, it would suggest that the pH should be around 2. Alright, considering that I need to calculate the pH, I will need the pH formula. And now that I have it, I'm going to substitute. And then I'm going to use my calculator. Negative log of 8.9 multiplied by 10 to the power of -9. And that gives me 8.0506 and so on. And so the pH of our seawater sample is 8.05 when rounded to 2 decimal places. What about the concentration of the hydroxide ions? Well, for that, I'm going to use the water dissociation constant. Recall that the Kw is the product of the hydrogen ion and hydroxide ion concentrations. Kw has to be 1 times 10 to the -14. The hydrogen ion concentration was given to us as 8.9 times 10 to -9. And it is the hydroxide ion concentration that we are trying to calculate. To calculate the hydroxide ion concentration, I need to divide both sides by 8.9 times 10 to -9. I will have 1 multiplied by 10 to the power of -14 divided by 8.9 multiplied by 10 to the power of -9. And that will give me this value. I'm going to round it to 2 significant figures and express it using scientific notation. And so I will have 1.1 multiplied by 10 to the power of -6 when rounded to 2 significant figures. That is the hydroxide ion concentration. Recall that the square brackets indicate molarity, and therefore the units are moles per liter. Let me do another one. This time we are given the pH of a sample of a soft drink, and it happens to be 2.58. We are asked to determine the hydrogen ion concentration as well as the hydroxide ion concentration. Before I proceed, please note that the pH value is unitless. It is just a number, whereas the concentrations of hydrogen and hydroxide ions will be in moles per liter. In order to solve for the hydrogen ion concentration, we need a slightly modified version of the pH formula. And here it is. The hydrogen ion concentration equals 10 raised to the negative pH. All I need to do now is substitute. 10 raised to the power of -2.58 gives me 0.00263 and so on. I'm going to round it to 2 significant figures. And so I will have 0.0026 when rounded to 2 significant figures. I can also convert this to scientific notation, and it would give me 2.6 multiplied by 10 to the power of -3. Now that I have the hydrogen ion concentration, I can use Kw to calculate the hydroxide ion concentration. Here is the general expression for the water dissociation constant, and now I'm going to substitute. Once I divide both sides by 2.6 times 10 to the power of -3, I will end up with 3.8 multiplied by 10 to -12 when rounded to 2 significant figures. In summary, when it comes to pH calculations, there are 2 general scenarios. Either we are given the hydrogen ion concentration and we need to calculate the pH, or we are given the pH value and we need to calculate the hydrogen ion concentration. Once we have the hydrogen ion concentration, we can use Kw to calculate the hydroxide ion concentration. That is all for now, and I will see you on the flip side.